All right, welcome to some new slides. We're actually going to finish these up and even start some new ones after these today, because this one's a bit shorter. But I do have some fun topics. All right, the first one here is containers, and it's all about holding stuff. So there are a bunch of different container classes in C++ that have been already implemented for us, and I'd like to teach you about them, because you will need to know how to build them. Well, you'll learn how to build them in CSCI 41, but you need to know what they look like, a little bit at least, in CSCI 40. Okay, so yeah, let's store some stuff. We'll see what C++ is given to us in the way of containing things. All right. So before we get there, though, I want to talk about the idea of an abstract data type. It's ADT for short. You're going to get very familiar with this concept in CSCI 41 if you need to take that class. So these slides are kind of preparing us for 41. All right, because this will be one of the first things we talk about there. And then, yeah, we'll get into containers because they're a type of ADT. Okay, so an ADT, abstract data type, it is, if you look it up in like a textbook, it says that it's a class of objects whose logical behavior is defined by a set of values and a set of operations, which is very, very vague. All right, but what I want you to think of it as is it's essentially like it's a class. It's a C++ class, more or less. An ADT we usually make a class that defines it, and it's like a black box. It's like a black box. You can't see through, can't really see what's going on inside of it, how it's working, but it's something you can ask to do things for you, and you understand what operations are involved. So an ADT is something that is defined in terms of its operations. All right, it knows how to respond to your queries, and though you can't see the gears inside, you're not sure how it's implemented, and maybe you don't even care. All right, so a good example of an ADT is a vector. So a vector, I haven't really told you what's going on inside of a vector, and maybe you can imagine a little bit what's happening. There are like arrays, kind of, in a weird way, on the heap secretly, but you didn't need to care, right? To you, as a CSCI 40 student, a vector is just it's a black box that can respond to your questions in a vectory way. You tell the vector, hey, dot pushback of something. You're like, dot pushback on like 2 or something, and it's like, sure, it's a void operation, right? Void method. And then you're like, okay, if that was the first thing you pushed back, then to be a vector, if you ask it next, like, all right, what's dot add 0? It better give you back 2, right? As long as it plays that game properly, the black box is a vector. Does that make sense? Like a vector, all it is, it's defined in terms of its operations. You have no clue if there's an array deep down under there. It doesn't even matter if there is one, right? Could be like a human secretly across a network connection or something that's like writing down your numbers on a piece of paper and like really quickly giving the answer back. You don't care how it's implemented as long as it plays the vector game, because that's what it means to be a vector. It's defined in terms of the operations that it can be, that you can perform on it. Okay, and it's just something you can ask, like, all right, push back, pop back, at, size, like all those things. If they work together properly in the way that you expect as a vector, it is a vector, even if it was like storing your numbers as strings or something, not even in an array. It doesn't matter. All right, so that's an ADT. And a container is a special kind of ADT. It's a type of ADT that holds on to elements in a fancy way. All right, so yeah, a container is a type that holds elements, and it responds to your questions in interesting ways, different kinds of answers and different kinds of questions depending on the container. All right, so yeah, a vector, for example, is a container. You can put whatever you want inside of a vector, right? It holds on to things. You can ask it to do stuff. So you can have a vector of vectors if you want to. That would be a multi-dimensional vector at that point. That's totally possible. A vector of ints. A 3D vector if you want to keep on going, right? A vector of vectors of vectors. So yeah, there's a bunch of different kind of container classes that have been pre-implemented in the C++ standard library, and we're going to talk about all of them, or most of them today. All right, you can go look up the rest. It won't be too hard once I show you these. All right, so let's start with vectors because like we're comfortable with them. There's some more pieces of them that I want to show to you today. They're iterators especially. All right, so vectors, we can go to the documentation, look them up, and be like, all right, a vector is, there's a whole container section, you see it? A vector is, this one. It's a sequence container representing arrays that can change in size. It's useful to read all these things. You're eventually understanding more and more. But like here's all the operations, and like one of those pieces is called iterators. I haven't really talked about those yet. We've used this for sorting, but that's about it. So let's talk about vectors and their iterators. So a vector it's called a random access container. What it means by that is like you can go to an arbitrary index of it very quickly. So They're random access. You can get to any piece of a vector very quickly by using indices. That's what it means. So let's say I've got my vector. There's a concept of indices. 0, 1, 2, 3, 4. That's what it means to be random access. All right. And like you can go to an index, get something out. You're like, all right, what's that index to? Or go change what's that index to. You're allowed to do that with a vector. It's random access. Okay. And there is a time complexity to all of these operations, because that's going to be the trade-off between containers. Like there's going to be how much time does it take to do these things. Like a vector.at to go and mess with an index. You scroll down, it's like, what is the complexity of that? It's constant. All right. Constant is the best time complexity possible. You cannot do better than constant. All right. And so a lot of vector operations, the ones that we like to do, are constant time, which is super nice. So .add is constant, getting the size of a vector is constant, and even pushback, surprisingly, to add a new thing to a vector is constant time. It's as fast as humanly possible, which is crazy. You'll have to wait till a four-year college's algorithms class to fully understand why pushback is constant, because it's a little weird even once you understand how to implement it. It is crazy. It's amortized constant. I won't go into what that means, all right? But that's kind of cool. Constant time, just to add something to the end of a vector as many times as I want. Each time it's constant. So cool. And yeah, you can use .at, .size to move around your vectors. But vectors also have a concept of iterators, all right? Iterators that move around the container for you. So you've got your .begin that gives you an iterator to the beginning, and .end gives you an iterator to what's really one past the end, if you remember my discussion on sorting. What are those? So just another way of going through the vector? More or less, that is the case. All right, so an iterator, it's an abstraction over iteration. All right, it's just a bunch of types and methods that are kind of modeled after pointers if you click on them. Like, hey, let's go look at an example of using v.begin. It gives you back an iterator into the vector, whatever that means. Here's like an example of it being used. You can use that to go through your vector. Like, all right, give me a vector int iterator to the beginning. That's the type of it. If it's a vector of ints and you ask for .begin, it's giving you a vector of int : iterator. It's like a type within a type. All right. And .end is one past the end, so you want to keep going until it's one past, and you can plus it like a pointer. You can go star it, star dereference your iterator. So it's overloaded all these operations, which is kind of weird. So we kind of think of it as like using pointers, even though it doesn't have to be using pointers really. It's like it's modeled after it though. So yeah, v.begin, it gives you back an iterator to the beginning of your vector. All right, whatever its type is. It might be a little weird, the vector of doubles versus vector of ints. It's a different kind of iterator, but we don't need to get into that right now. So here, let's say that this is my vector, 8, 6, 7, 5, and if you ask for v.begin, and you save that into like a variable called it, like these people were, what happens if you say it equals v.begin, after you've declared it and given it a type, it equals v.begin, what will happen once you run this line, it will be set to essentially a pointer to that first element, all right? And the type of the iterator it depends on the type of the original vector. So it's like a type within a type. The type of v.begin, if it's a vector of ints like this one, then it's vector int : iterator. If it was a vector of doubles, it would be vector double : iterator. That's the type of an iterator. That's what begin gives you back, okay? And then v.end is the other side. It's an iterator to not the normal end, but one past the end of the vector. It's somewhere you never want to go. So here is like the idea of where v.end would take you. So v.end would give you back an iterator to right here. So you never want to actually go there. All right. You don't want to dereference that one. It's like null dereference almost. But you do think of iterators as pointers, and you can say like, all right, star it. You can be like, you can dereference your iterator whenever it's anywhere. And star it right now, so looking at the 8 place, it will give you back the 8 and give you back that int. And then you can advance your iterator. You can be like it++. It's hard to differentiate now because you've got t's and pluses right next to each other. So I'll use curly letters. I'll do my best. it++. You can run that code, and that will advance your iterator. Like, all right, it's not pointing there anymore. It's pointing to the next thing. It will go in order from left to right. All right. So that's what iterators are all about. They're kind of like using pointers. All right. They're an abstraction over the idea of pointers and pointer arithmetic, even though they don't have to be implemented that way. All right. So let's see. yeah, let me just show you an example. It's kind of like this. That's worth it. So this is lecture. I think this is the right lecture, right? Yeah. I'll make a new file, just called, I guess, vectors. That's the one I want to write. And so I better include the vector library, of course. And yeah, let's make my example vector. Vector int v is just that one. 8675. Okay. So there's my vector. And yeah, let's ask it for iterators. We can say, all right, give me v.begin in v. The type of that, if I call it it, the type of that iterator it is a vector int : iterator. It's an iterator to that specific kind of vector, a vector of ints. All right, so that's, you got to keep that in mind. It's a weird long type, which is unfortunate. And then once you have it though, v.begin is essentially a pointer to the first element, the first thing in your vector. It's trying to iterate through it if you let it. So cout star it will give us the 8. See? So there it is. And then you can advance the iterator. You can be like it++ to advance it, move it over by 1 to now point to the next thing. And then if you do star it again, now it's pointing to the next element. So it'll point to the 6. And if you star it, it should give you back the 6 now. And you can use that to set the value as well. You could be like star it equals something. Equals 7 or whatever you want. That's allowed too. So that's a thing. And you can use this in a loop to iterate through your vector. You can be like, all right, for vector int : iterator it equals v.begin. And you just want to keep going until it's the end, right? You'd never want to get to 1 past the end though. v.end gives you 1 past the end, so you want to just keep going as long as it is not equal to v.end. That's what you have to do. There's no real concept of like less than, so don't do that. It's got to be not equals to. It's like an address comparison almost. Think of it that way. And then it++ to advance it, right? And so now inside the body, you'd be like star it. Print everything out with a space. So the types are weird. It's a little odd looking, but I hope you see what's going on there. You see it printed out? Just another way to go through your vector. And this seems disgusting, I know right now, but the beauty of iterators is that these types have been made. Iterators, begin and ends, have been made for every kind of container inside of C++. That's where the power lies. All right. And then also the range-based for loop. You remember that one? That's a way to go through your vector from left to right. You'd be like, for every int x in my vector v, do something with x. Secretly, this syntax is translating into a use of iterators. This exact code right here turns exactly into this for you. Isn't that cool? So the range-based for loop is really using iterators. It's using this under the hood. It's doing the v.begin, v.end, all that stuff for you. The dereferencing. So the compiler is turning this code into this code. All right. I hope that makes sense. That's pretty cool. So yeah, here let's kind of talk about what's going on when this loop is executing. How I want you to think about it, at least. You can think of it as secretly using pointers, but it does not have to be implemented using pointers. It's just a class. An iterator is just honestly a class. So it's just a type that's overloaded the pointer kinds of operators. But let's think about it, at least in terms of pointers, just to remember about pointers, I guess, at least. So here's my vector. Here's what I want you to think about what iterators are doing for you. So like, instead of indices, 0, 1, 2, 3, let's think of addresses. So let's say that the vector starts at address 100. If it's a vector of ints, then the next int is 104, then 108, then 112. 1 past the end would be the int at address 116 that we can never go to. It's not part of our vector. Yeah. And so at the very beginning, what happens is it equals v.begin. Think of it as pointers. Like it starts out holding the address 100. That's the first thing. So it starts out pointing here. And then as we use star it to print stuff, like star it to print out the 8, it'll just dereference, get the thing at that box in memory. And then it++ advances the pointer by an int worth of address, not to 101, but to 104. All right, because you're advancing an int pointer. It goes to the next int. So it chops it off, goes to there. Now it's pointing here. Star it again. That's why you get the 6. Star it++. That's what's going on. All right, and that's why you get, then it goes to 108, right? pointing there. That's why you get the 7, IT++. Make it 112. Now it's pointing there. That's why you get the 5 when you star the IT again. Do IT++ one more time. Now it's 116. Now it's pointing to no man's land. You want to stop as long as that should keep going as long as it's not equal to v.end. All right, that's it. That's how you can think of it secretly using pointers, though it technically does not have to. Ask me more about that if you'd like in office hours. I don't want to confuse everybody, but think of iterators, at least for now, as using pointers. And yeah, let's talk about some more container classes now. So remember lists? Lists are a container in C++ pre-made for you. It's a wrap around the idea of linked lists. All right, and this is a great example of why would I ever want to learn this weird syntax when I could just use indices? Well, some containers don't have indices. All right, even though it's complicated. Iterators are going to work exactly the same for completely different containers. So lists are another ADT in C++. So you got the list header. It wraps around the idea, if you read this, it essentially wraps around the idea of a linked list. Remember that? So like you can have a list that holds stuff. Let's say I wanted to hold my 8675 again. It looks completely different as a linked list, right? 8675. Completely different as a linked list, but I'm still going to get an iterator, and I can still go through it in the same way. Right? It's going to work the same way. It's going to be great. So yeah, there's a list ADT that wraps around the idea of a linked list, like what you can do to a linked list very easily. You can add to the end as well as to the start of a linked list very easily. There's a push back as well as a push front. There is no push front for vectors. See those? There's a pop front as well. That's pretty cool. You had these from vectors, but lists give you the ability to do other things very quickly. And they're constant time too. All right. So get the size, all these things, these commands, push back, pop back, get the size, insertion and deletion to the back or the front are constant time. There is not even a push front in vector land. And if there was one, you'd have to shift everything over. It would be linear time. But complexity for linked lists is constant, because to make a new node, do some weird heap stuff, very simple. Very, very simple. Constant time. And so there's a trade-off. You want to use lists if you want to add to the front and the back, and remove as well. Okay? So let me make a list for you, showing you the push back, the pop back, all that fun stuff. We'll use the list type. It's the list container. Lists.cpp. And so we'll include list. All right, and so you can make just as easily a list of ints called L. And now it's empty. You can start adding to it, like pushback, L.pushback, 3, 4. Oops. So now it's the list 3 and then 4, right? And now let's make it 1, 2, 3, 4 by adding to the front as well. Push front 2, push front 1. Do you see how now the list is 1, 2? Those are at the front now. 3, 4. Can you see the order in your mind? And even though I made it weird, right? I made it weird with all these push backs and pop backs. Their lists, by the way, are not random access iterator or not random access containers. There is no .at for lists. You have to go through, right? You have to follow these pointers deep down to get anywhere. But you can still use iterators, even though there's no .at. You get an iterator. All right, so they work exactly the same way. You still then get to use the range-based for loop. That still works perfectly because it's being translated into iterators. You can do this. You can be like, all right, here's the list that I made, right? It was 1, 2, 3, 4. Under the hood, you don't have to know this. It's just an ADT, but it really is a linked list. It looks like this. And if you want to go through it, you can use iterators. You can be like, all right, IT equals L.begin. That'll set like a pointer to this node, just like that. And then you can be like star IT. It will give you back the thing at that node, the thing in your list right now, where you are looking. And then you can say IT++ to advance it. Like, all right, now we're looking at the 2 node. And you can keep going. IT++, star IT, IT++, one last time to point off into nowhere, like or list.end is probably like the null pointer, because that's where you get if you go too far, right? That's how you run into the end. So that's lists. Isn't that cool? And so you can use an iterator on lists very easily. They're still the begin and end. They're all still there, even though there's no .at. Still go through a list in the same exact way. Do you see it? Now it's just a list of ints, : iterator. Everything is working exactly the same. It's so nice. So let's do that. For list int iterator it, so type within a type, equals l.begin. L is not equal to L, sorry, it is not equal to L.end, it plus plus. And then what do I want to do? Let's just like print it all out. Say out star it and a space. And that'll go through the list that I built up. It's going to be 1, 2, 3, 4. And print it out. Even though it looks nothing like a vector under the hood, we still have the iterators made for us, and they work the same way, which is great. And that means, again, the range-based for loop works the same, works perfectly, just like it did for vectors. It works exactly the same because it's being translated into a use of iterators. Like for every int I in my list L, like that'll be translated into exactly this code if I do the same stuff. Cout I and a space, and then a new line. So this loop is exactly, it's turned into by the compiler exactly the same code as this one. And now you know what's happening. Now you know the secret. That's why it's working twice. That's really cool, I think. All right, so that's lists. It's another kind of container, holding stuff. It has the ability to do other things than vectors a bit faster, right? Some things that vectors can't even do. Add to the front, delete from the front. You can do it super fast. So these are competitors, right? Let's keep going. There's others. There's one called set. It's got the set header, and I encourage you to read all this. We've got a constructor, whatever it does, it's got iterators. Isn't that cool? So a set, what it does is like you give it a type, like a set of ints, a set of doubles. It stores unique things of that type in an order, okay? So in a set, you can add stuff, you can insert stuff into your set, you can see if it was there by counting if there's anything, like it's either ever going to be 1 or 0 because it stores unique things, but it's still called count. Like count if there's any 2s in my set. It's either 1 or 0, it's either there or not there, and then there's also erase, you can get rid of things. And it also keeps track of order. All right, so let's say I've got a set. Think of it as like a cloud that's holding stuff. It has an order to it all, though. And let's say that you want to insert into your set in order like 2, 2, 1, 3, and 0. You want to insert all those things. So the first time you insert the 2, it's like, okay, that's a new thing. I'll put it there. Then you put 2 again, it's like, all right, it's already there. I'm not adding it again. So sets do not store duplicates. Lists and vectors do, sets do not. It's just, it only cares if it's there or not there. And then 1, if you add the 1 next, it's like, okay, yeah, I'll add the 1, and I need to remember that it's smaller than the 2. So it does keep track of an order. And then you add a 3, it's like, that's new, I'll put it after the 2. You add a 0, that's new, I'll put it before the 1. So it keeps track of an order secretly, all right? And to do that, it's not going to be constant time because there's ordering involved here. It is, though, pretty much as fast as it could be. It's called logarithmic time. Just like that's binary search levels of speed, which is very fast still. That's pretty cool. So yeah, let's click on one of these, like sets insert on a set, adds a new element, and what it will do is just put it there. Put it in your set if it's not there at all. All right, so it's logarithmic in size to add a new element. So for example, if I wanted to add another value to my set right now, it would take about log base 2 of 4, because that's the current size, log base 2 of 4 basic operations to do an addition into this set now, because it's got some things, it's got to figure out where it all goes. All right, so it's really fast, honestly, because you're getting order out of the deal. That's super duper fast. Logarithmic is as good as you can do here. All right, and you get order out of it. It's so nice. All right, and you'll see that when you iterate through. If you ever iterate through your set using iterators, it will tell you if it's like, it will give you back the order. That's like the sorted order of everything. So that's really nice. Let me show that to you. So you got to include the set header, and let's make a set of ints. All right, and let's add stuff. Let's do exactly that order. So 2, insert 2, oops, 2, 2, 1, 3, and it was 0 after that. Okay, so there's all this stuff. And then you can ask it, hey, it's like sets are all about saying if something was there or not there. So you can say, hey, was it there? You say count, to count how many things are in the set of that particular value. So like count all the 2's. How many are there? Are there any or are there none? That's pretty much it. So here, let's do counts for 2 and 1 and for 42, something that's not there. It's only ever going to be 1 or 0, because sets do not hold duplicates. And I said sets plural. Okay, so yeah, it's like, you can use it as true or false as well. It's like 1 if it's true, 0 if it's false. Like, is it there or not there? Count it. Even though I try to add 2, sets only take 1. There's no duplicates. So there's a 2 and there's a 1 in the set, but there are no 42's. It's not there at all. So that's kind of nice. You can use that in an if statement, because like any number that's non-zero is true, any number that's 0 is false. You can use that as like true or false. Like, is it there or not there? Count. Okay, so there's that one. And then also you can use iterators to go through your set. Exactly the same as you've been doing it for everything else. Like, all right, for set int iterator, it equals s.begin. It is unequal to s.ends, 1 past the end of the set, it++. And like, this is implemented under the hood in a very weird way. You'll have to wait till CSCI 41 to understand it fully, or even at all, but still the iterators have been made for us. We get to use it in exactly the same way, which means we also get the range-based for loop if we didn't want to do this. It's just amazing, right? So that's iteration through sets, and it's going to give you back things in the order that you put them in. Isn't that cool? So sets are a good ADT for like keeping track of if something's there or not, and you don't care about duplicates. And then there's also a sense of order as well. If you want to get them all out in order, you can do that. Okay, so that's sets. There's one more that I want to talk about, one more container type. It's called map. It's very similar to sets, but instead of just storing one thing, it stores a pair of things. All right, so a map stores pairs of values, but they're ordered by the key. All right, there's 2 kinds of things that you put in a map. There's a key type and a value type. And we say that a map maps keys to values. So it looks like this. It takes 2 things, 2 types in, where is it? There it is. It takes 2 types when you're defining it. It takes a key type and a value type. Where is that? Is that way over here? Whee! That's a little large. Sorry. But here, let me just like go down to an example with like the constructor, for example. Here's a map of characters to int. So it takes 2 types. The first thing is the key type. The second thing is the value type. And let's talk about what that means. So a good example of a map. So key type, keys are mapped to values, we say. A good example of a map is like a phone book. Do we all know what a phone book is? Because they don't really exist anymore. It was just a big book that was alphabetized that you could look up somebody's name and it will give you their phone number. So in terms of keys and values, the names of people in a phone book are the keys, because like you can flip through the phone book, it's out of alphabetical order. You can quickly find who you're looking for, and it will map their phone number in order to it'll map their name in order to their phone numbers. So that's what it's doing. It's mapping name strings to their phone numbers, integers. Does that make sense? So that's the key type and the value type for an example phone book map. And what you do, like if you have a map, it's just like a cloud of things again, and you can store those pairs, those key value pairs. You can put like, all right, in the phone book, let's add my name and my phone number. I don't know if Fresno does phone books anymore, honestly. Maybe. Like you can store it just like that. So it's going to store it ordered based on the keys. The values don't matter at all about ordering. It's like it's going to order them based on the keys, but like you have access to this. All right, you can look it up. You can look up somebody's name and get out their phone number. Let's say maybe I give my cat a phone number. So Alonzo's number will be the next one. Okay, so that's what you can do, and this is the key. You can use that to look things up. It's called the key. And let me rewrite that. And I still don't like the way I wrote it. Key, there. And then this one is the value that's being mapped by the key. And so the whole point of using a map is that you can look up the value that's associated with each key. So you're like, hey, go look up in the map Lawton. It will give you back the number. Hey, map, go look up Lonzo. It will give you back his phone number. Okay? And they are ordered based on their keys, though. So like it's alphabetized if it's a bunch of strings. And so, yeah, maps have the same time as sets, because it's essentially doing the same things. Like looking stuff up is just like, instead of saying yes or no, it's there or not, it's like giving back the value instead. So it's still logarithmic time, just like binary search was, still pretty fast. Okay. And yeah, I think that's all that I want to show you. Of course, there's an iterator. The iterator, though, will give you back, well, here, let's just do an example real quick, and then we'll talk about it some more. So maps, because the iterator is a little bit different because it's got two things now. It's a pair of things. Right? It's mapping two things. So let's have a phone book example. So it's going to be map from strings to ints. So map from string to int, call phone book. And let's start adding stuff. To add stuff into your map, it's there is a dot insert, but it works weird. It takes a different type. You can say dot in place to put things in and give two arguments. You give the key and you give the value. So there's mapping to my phone number. And then same for my cat. All right. So that's how you add stuff into the map. And then you can again use like that dot count to see if there was a key. It's always based on the key type now, because that's what you're using to look stuff up. Look up things with the key. And so there's still a dot count to see if something's there. Like, is it there or not? Is that key somewhere in the map? It's only ever going to give back 1 if it's in there, or 0 otherwise. But like they try to keep this dot count the same across different containers, just like they keep begin and end the same across containers. That's why it doesn't make a whole lot of sense to call it count here, but they're trying to be universal, I guess. So it's always in terms of the key types, like phonebook.count. Hey, are there any Lautins in the phone book? And that's how you should always do that to make sure it's there before you go look things up. And then like check if my mom is in the phone book. And so like you should always be doing a check to make sure it's there before you look it up, because it'll throw an exception if it's not in there. And you try to look it up. So yeah, Lawton's in there, but my mom's phone number is not in the phone book. It's always based on the keys. And then once you know your key is in there, you can go look it up. You can be like, phone book, it is .at, right? Just like for strings and for vectors. Instead of indices, it's go to that key. Phonebook.at Lawton, it gives you back the corresponding value. Isn't that cool? So that's how it works. That's super neat, and it's very fast, efficient. If you go look up somebody that's not there, it will throw an exception. So that's why you should always check with the dot count to see if it was there, because it's going to throw an exception otherwise. And yeah, just like everything else, there is an iterator for maps. There's a begin, there's an end. I don't remember if I said this or not. I think I glazed past it, sorry. For a lot of types with iterators, you can go backwards. It's totally possible to go backwards. There's like IT minus minus if you wanted to. There's also like reverse iterators. There's reverse begin, reverse one past the end. Like you could use those. Look into that. Click on those if you'd like. But I'm just teaching the normal begin and end right now. For maps, begin and end, their iterators IT. It's not pointing to the element. It's pointing to a pair of things. Pointing to a pair. And so you need to be able to get out the first thing in the pair and the second thing in the pair. And that's actually what they're called. All right, so it's you're getting back a pair of things. That is a legitimate type in C++. It gives you back a pair from key to value, and inside of every pair type thing, you can get the first and the second. Those are your member variables that you can access. So it's easier to just show that to you. Here they are doing it. It's like you got a dereference to get to the pair, but then there's a first thing and a second thing. So people are using the arrow operator for that. Okay, so here. Code is worth 1,000 words. So let's do it again for map. Map string int iterator, right? It's always based on the type. Lives within it. Equals it's not m, it's phone book. Dot begin. IT is unequal to phone book. Dot end. IT plus plus. There it is. And what do I want to do with each IT? I want to output. It's pointing to the pair now. I got keys and values. I got a first and a second. So cout, it's not just star IT anymore. It's like once I'm at star IT, it's a pair of things. It's either the first thing, like that's the key, and we want to print out like that's mapping to the value type. And so instead of star IT dot second, you remember the shorthand? You can do the arrow operator. That does the dereference and the dot for you. All right, so that's what it's doing. We're just doing IT plus plus there. It's a lot of words, and that's going to go through it. And again, there is also a concept of a range-based for loop on maps. It'll turn into this though. And so here it is. It's going through the phone book in order. It's in order by the keys, and it's showing me their corresponding values, the first thing and the second thing. All right. So most of the time, what you use maps for is just like to get back the thing that you put in, like go and look up something very quickly, because it's very fast to look up a value associated with a key. Okay, so that's maps in a nutshell, and hopefully it's all making sense. So you've seen a bunch of different types now. We've looked at vectors, we've looked at lists and sets and maps, and so you have a nice treasure chest of different containers that you can use for a bunch of different things. I want you to pause the video and consider all these things, right? Which container out of these, vector, list, set, and map, would you use to store Pokemon cards and their selling prices, a bunch of people, like a representation of people waiting in line, like maybe at Disneyland or something, a bunch of students on a roster for a class, and then the last 100 days of Bitcoin prices. Please pause the video, think of like which of these would apply and which ones would be best. There is not one right answer. It really depends on how you're going to use the data. All right, so you have to think about the use case for sure. And yeah, I'll give you my ideas after you've tried. It's really useful to think about this. So yeah, it always depends. So like for Pokemon cards, you can put this in any of these, but like it depends on what you're going to use it for. So like maybe you want to be able to map the names of the Pokemon to their prices, like map Pikachu to its price. That would make sense to do it like that. Or you could have like a vector of pairs of names, right? Vector of Pokemon names and their prices, so that you can like easily sort by their price very quickly. That would make sense. Okay, stuff like that. I think vector and map would make the most sense for those. For a group of people waiting in line, maybe if you want people to be able to cut the line, like list might be the best, because you can push front as well as the back. Like if a famous person goes to Disneyland, they get to cut the line or something, or if you have a fast pass. So you might need access to the push front as well as the push back. But if everybody's playing fair, then a vector might be worth it, right? You can map people to their like place in line, their corresponding wait time or something. Like there's different ideas here. I hope that makes sense. And then students on a class roster, it's up to you. Like a vector, if you want to just put them in order. A list, like a set, would order them by last name, maybe. That would work. If you want to do attendance, maybe you can map their name to here or not here, true or false, for a given day. It's really up to you. And then last 100 days of Bitcoin prices, probably a vector. I don't know, if you want to like just see it all in order, like be able to just like look at it all at once. A vector might be useful because you can go to an index very quickly. Lists would make it harder, but you'd still get the order. Set probably doesn't make any sense at all, but map might. You could map dates, like a date value, like a certain day of the year, like an exact date, 2/15/25 or whatever, to the price on that day. So like a date type mapping to a double type for price. That would work. So you do have options, and it really depends on the use case, but hopefully by thinking about that, you can see what might work for you. All right, so you have options now. So that's containers in a nutshell. I hope that was fun. That's the cool ideas, right? Cool stuff to think about. And that brings us to the end of these slides, but we are not done today. All right, I have one more thing to start talking about. We're not going to get finished with it, but it's a very useful topic. I want to talk about the world outside of C++. All right, I will not test you on this, by the way. This set of slides from here onwards, until we finish, I'm not going to test you on any of this beyond C++ stuff. Just, this is good information. You still need to watch this lecture, the rest of this, because you may be transferring to a school that required you to know Java or required you to know Python, because that's what they taught their students in their version of CSCI 40. All right, that is totally possible. A lot of UCs, for example, they teach Python first. So I'm going to teach you those two languages in this class. I have a set of slides. I'm going to teach you Java. I'm going to teach you Python. All right, we will get through them together. You will find that it's not that bad. Once you've learned one object-oriented language, it's very easy to learn the others. But yeah, I'm going to teach you some other languages now. It's not something I'm going to test you on, but it's something you should know. All right, you need to keep paying attention, because you're going to need to know multiple languages one day. All right, it might be soon after you transfer. Okay, so let's talk about Java. So yeah, there's a bunch of useful tutorials. I encourage you to look up them all. I'll give you just a sneak peek of Java today. We'll do more next time. But here is the Java language. Here's a nice little website. It's called learnxandyminutes.com. They have a page on Java and a bunch of other things. It's just a big long page with an example file that's just kind of walks through all the different things in Java and how you use it. All right, you can see like the code. There's semicolons. It looks very similar to C++. They got for loops. You scroll down, you like learn more and more advanced things, but and they have more examples and places to go next after that. But it's a good like initial view of the Java language. I encourage you to read this website. It's very similar to C++. It is an object-oriented language. It was invented after C++, if I remember the order correctly. But yeah, it's going to look very similar. It is very heavily object-oriented. They focus on classes much more than C++, because you know that you can make a C++ program without ever having to make a class. In Java, that is not true. So yeah, let's talk about it. I better show you Hello World for sure. So yeah, let's make a program. I will then let me just make the Hello World program in Java right now, and then I'll talk about it and mark it up with comments afterwards. Okay, so I'm going to make a file, a new file, call it Hello World. They like to use capitals a lot in Java and camel case, and it's not .cpp because it's not C++. It's .java. That's what they use. All right, and so let me just write the program, then I'll explain it. Public class Hello World, and then it's public static void main string with a capital S bracket bracket args, and then it is system dot out dot println hello world between quotes. There it is, semicolon. There's your program. There's your Hello World program in Java, and let's compile and run it. So there is a compiler in Java. It's called JavaC, Java compiler. It's what it's short for. What you do is you just give it the name of the file. You say JavaC that file. So oops. So there's my Java file at the start there. I say JavaC, give the name of it, and what it will do if there's no errors is it produces a class file, helloworld.class file. All right, and then this is not a file that is runnable on the CPU yet. So Java is compiled in a weird way. It needs a virtual machine to be run. It's called the Java Virtual Machine, or the JVM for short. You have to run the program within Java, and then it will convert it on the fly to real CPU instructions. So you have to run it through Java. You say Java space, the name of the program without the .class, so just the hello world part, and that will actually run it. Okay, so say Java hello world, hit enter, and there it is. It ran. Cool. So that's your first taste of Java. It looks a little weird, but that's a good start. All right, so now let me mark it up. Let's talk about what all this means. So you have to make a class, surprisingly, to just have a main function. All right. So really, this is a main method, but it's a static method, which makes it a act like a function. All right. Let's talk about this. So in Java, I put the comma in the wrong spot. Off to a good start. So in Java, everything is a class. All right. So if you just want a function, you just want a main function, you make a static method inside of a class. All right. If you just want a function, you need to put it inside of a class. All right. Inside a class. The word static makes it part of the class itself and not a normal method. So go back to your textbook. I know it says something about static somewhere in the classes chapter, so please go read that. Search for it in your textbook. Understand that it acts like a function. All right, that's as good as you get in Java. So this hello world class, we mark it as public. There's no public colon or anything. It's just like you got to put the access modifier next to everything. Public, private. So hello world is public. So it's visible to the outside world. So the class itself gets to be public or private if you say that. And that means other people could include our library and use it, our Hello World class, and use it. That means other people could import it. So we say import in Java, it's not include. Import it and use it. Okay? And then here's the main function. It's a static method really though. So the main function, in quotes I guess, is really a static method. It lives inside the public class associated with this file. You have to say exactly this. It's always, there's no like, can't do anything. You always give the command line arguments. This string bracket bracket args is a string array. I like that the array part is next to the type. I prefer that. And then its name is args. You always have to say this, right? You must use that definition even if you're not using the command line arguments like we aren't. args are your command line arguments. You have to use it even if you're not using them. Okay, so there's that. That's one thought. And then, yeah, in Java, your command line arguments, it's not an array of C strings, because this has nothing to do with the C language anymore. In Java, your command line arguments are, args, is an array of strings. All right, so string, they use capital S for their strings. And yeah, main is a public method inside the hello world class. So we started marking it with public. It's also static. And that means it belongs to the class itself rather than to any instances, rather than to any objects of that class. All right? Which means that it belongs to the class. Go read about that. Static methods exist also in C++. Go read about it in your textbook and understand that it functions for all intents and purposes. Every static method is essentially a function, all right? Because of that. It belongs to the class itself rather than to any object of the class, okay? And so yeah, there's that. And then also, if you're ever going to write a bunch of functions or methods, you don't have to declare them. There's no concept of separate declarations in Java. There's no header files or anything either. So you don't have to declare any functions or methods in Java. Like you put them in any order, and it'll just find them for you. All right, so it just finds them no matter what order you put them in. All right, so there's my marked up thing. So Java has the same kind of comments, still / for comments for us in Java. So I hope that makes a little bit of sense. And also, when you make a file with a main function and like a public class, every file has to have a public class in it. You can have multiple private classes in addition to that. But if you say your public class of this file is called hello world, it must live in a file called helloworld.java with the same capitalization. If I mess any of that up, I get a compiler error. All right, it has to be called that. You'll get a compiler error if you don't. Okay, that's kind of neat. It keeps track of, now you know exactly where that class lives. It has to be in a file called that. So that's pretty cool. That's your first taste of Java. And you can see that's a little wordy. Like their cout is this println method, static method. Or no, sorry, it's not a. It's a normal method. It lives in the system package. They call that instead of header or library. It's the system package. There's an out object that's like their cout. And like on that we can say, hey cout, or hey output, please print a line and break that line. So that's what it's doing there. All right. So println means print as well as break the line after you print. So that lives here. Let's look it up in the documentation for Java. So it's got a bunch of stuff in the Java library. So you've got here all your packages. There's a bunch of them. The library is next level, guys. It's much better than C++. And here, like, here's all the classes that exist inside of Java. It's amazing. So here's the system package that I've gone in on. It lives in the java.lang package. All right, there's a system thing. Where is that? There's a system, I guess it's a system class, sorry. The real package is java.lang. It's just like default imported for the Java language stuff, like baked in, stuff that you always get. There's a system class, and then the system has a static print stream, it's called, object called out, just like cout was an O stream for C++. And then every out object is a print stream, and what can you do to it? Every print stream has these methods. There's print methods for a bunch of different types, like it knows how to print a bool, a char, a double int, so all these types are very similar. And then it knows how to do println. So we just called the one with strings, println with a string. There you go. All right. So it is a little wordy, but they have really good documentation. All right. Really good documentation in Java. I love it. So yeah, there's your first taste of it. Let's talk a little bit more about all this stuff. I'll make one more file for the day. So yeah, pretty much everything is a class in Java. There's also no pointers, though you do have to use the heap for a lot. It just like does it for you. It's going to handle the heap memory for you. And then arrays look slightly different. So there's a bunch of things. Let me just give you some examples like ints, doubles, bools, strings, and arrays. For their bools, they spell it out. They call it Boolean. instead of just bool. And for string, you know that it's capitalized now. So let me show you all that. I'll call it more Java.java, and you know that means that the public class better be called more Java in order to work. And then for a main function, it's public static void main string bracket bracket args. All right, even though I'm not going to use them. So yeah, to make variables, it's exactly the same. Say the type, give it a value, int x equals 42, double y equals 3.14. Instead of bool b, it's boolean b. And it's still true or false with lowercase. And then strings, capital S. No extra library needed. It's just like those are your Java strings. It's baked in. There's only one kind. All right, so there's that. Those are your normal types. Let me show you arrays, because arrays are a little bit different. Everything fancy, every object and array is made on the heap. So arrays must be made on the heap. And as you see up here, the bracket bracket part, you still use the brackets for arrays in Java. The bracket bracket goes after the type. It's part of the type. I like that. So the that goes after the type, and here's kind of what it looks like. Int bracket bracket r. You don't just say equals 1, 2, 3. It needs to be made on the heap, not the stack. You say new equals new int array, and then you can give the stuff. So it's going to be made on the heap, even though there's no pointers anywhere. All right. There's no concept of a pointer in Java. It just kind of does it for you, even because you're kind of forced to use the heap a lot more than you would in C++. So that's interesting. So it's doing that. And then also, all arrays know their size. So there's a concept of a vector. This is not a vector. This is an array still, but arrays in Java know their size. That's really nice. It's the name.length. That's like a member variable. So that's pretty cool. I like that. So let's see here. There's a weird order to what I want to say here. So yeah, all arrays on the heap, you have to use new to make one. And now let me just compile and run this for you. You still have for loops. For int I equals 0, I is less than r.length this time, I++. And then if I want to print all the elements in this array, it's going to be what? System.out, right? System.out.print ln r of I. So it's all very similar, all right? So there you go. There's a first program, or a second program. We say to compile again as javac, the Java file, and then it makes the .class file, and then you can run it. You can run the main function or static method in there by saying Java space that. Java space more Java. It goes and finds it and it runs it for you. So there it is. Cool, huh? So I hope that makes a little bit of sense. It is all slightly different. All right. So let's now talk about what's going on under the hood. So there is no /. We said Java more Java. We ran our program, our compiled program, right? Our .class file. We ran it in Java still, which is a little odd. It's different to C++. So what I want to say is that Java runs on what's called a virtual machine. So when you compile something, you're not actually ready to run it on your actual CPU. So here's kind of what's going on. We made our more Java.java file, and that looked like English. That was our code. That was not something that the computer could understand yet. Public class, you gotta compile it. Blah blah blah. We gave that to javac, and that made the .class file. And that made more Java.class, and that is a binary format. That is something that is closer to bare metal, but it is not runnable yet. All right, it's called Java bytecode. Bytecode. It's not actually machine code. It's something that's compiled in a way that lets this same compiled file run on any CPU. That's Java's trade-off. It's like you compile once and you run everywhere. That's their slogan. All right. So compiled Java programs, they can run on any computer where Java is installed. And that is very, very different to compiled C++ programs, because those are tied to the place that you compiled them. They're tied to the operating system and CPU architecture combo. And so if you're on the class server, for example, and you compile a C++ program, you cannot bring it into Windows and double-click it or even run it on the Windows terminal. It's not ready. It's not going to work, because on our class server, it is a Linux ARM architecture. That's different from like a Windows Intel architecture. It's very, very different, all right? And so Java's trade-off is that, like, all right, it's not yet runnable, but I can give this to anybody, and it will run as long as Java's installed for them, all right? So that's their give and take there. It runs almost as fast. but every program needs to be run in Java on the Java virtual machine. All right, so it's a little black box. You give your program to the Java virtual machine, and that's where it runs it. That's called the Java virtual machine. Or the JVM for short. And you have to have that installed on your computer in order to run a Java program. It will run the code for you. It will translate this byte code on the fly. It's very cool. I had to wait until a graduate level class after I got my bachelor's degree to fully understand what's going on. It's called a just-in-time compiler, which is really cool to think about. It runs the code for you. It translates it to your architecture, to your operating system on the fly as it's running, which is wild to think about. And so because of that, it is slightly slower than the equivalent C++ program, but on average, it's almost the same. Slightly slower, but pretty much at the same speed as a C++ program. All right, so there's that, and now you understand it. And because it's running on the JVM, it's like running the code for you, it's doing some stuff. It's actually making your life slightly easier than in C++. So this is why we teach C++ here instead of Java, because notice I made something on the heap with new. There's no concept of pointers, because like you do new a lot for Java. There is no delete. There is no delete in Java. It doesn't even exist in the language. Java is called garbage collected. When you say new, it builds something on the heap for you. It's like you got a heap still. More things need to be made on the heap in Java. So you made a bunch of stuff on the heap. It will just figure out, it's able to tell, the JVM is able to tell when your heap memory is no longer accessible, like your function's returned or something, you no longer have access to it, it's like leaked. It's impossible to leak memory in Java. It will call delete for you. It's like when something goes out of scope or you don't need it anymore. It just notices that. That's really cool, right? That is really nice. It will call delete for you. That will create some bad habits, and that's why we teach C++ first, right? So you've now learned to clean up after yourself. Now you can play the game with Java, right? So no delete is necessary, which is nice. Java takes care of deletion for you. There isn't even a delete in the language. It just notices. It notices. The garbage collector notices. That's a fun phrase, right? That's a fun metaphor. It's like a garbage collection service coming and watching your program. It notices when we're finished with heap memory, and it garbage collects it. Okay, that's what's going on, and that's why you never have to say delete in Java. You just say new. It will figure out when you're done with all of your memory. Okay, so yeah, I think that's where I want to stop for the day. You've learned about a brand new language, which is cool. I encourage you to read this little helper tutorial. There's plenty of other things on the internet too. The meme for Java is that it is very wordy, and so that's why you see this, and the system.out.println, you kind of got a taste of that already. There's more to it, but I guess the trade-off is you get really nice libraries. Even though they have long names, you have a lot of cool libraries in the Java language. So I'll show you some of those next time, and I think that is where I want to stop.